Phillips here again, making another video for A Level Biology on enzymes. And this one is looking at enzyme action and pH. It's also looking at the effects of concentration and enzyme inhibitors. So, just to remind you what pH actually is, pH is a measure of the hydrogen ion concentration in a solution. So the higher the hydrogen ion concentration, because acids are proton donors, they are more acidic the solution is, and the lower the pH is. Acids are called proton donors, and when they dissociate in water, so when they're dissolved, they're called this. If you look at hydrochloric acid, when it's dissolved in water, it always fully dissociates to release all its H plus ions and obviously Cl minuses, and that's because a strong acid or weak acid only partially dissociates. Above pH 7 is called an alkaline, and pH 7 is obviously neutral, so that's what you should know from GCSE. So, how then does this affect enzymes? Well, if you know about the structure of the secondary structure of a protein, you've got the alpha helix structure, and the alpha helix structure, as well as areas of the tertiary structure, are greatly held together by hydrogen bonds. You have slightly negative molecules and slightly positive molecules with hydrogen bonds together, which allows this spiral shape of the alpha helix structure to be held together. And the same with the beta pleated sheath, that's held together by hydrogen bonds as well. So what happens is, if we add into the solution, if we change the pH of a solution, let's say we put it into something that likes a neutral pH into a highly acidic pH, that is adding extra hydrogen ions to the solution. So what will happen is those hydrogen ions which aren't part of the protein then might start interacting with the charges on the protein, altering where the hydrogen bonds form, and thus causing the protein, instead of having hydrogen bonds here, then the hydrogen bonds will go out to the outside molecules, and that could cause the tertiary structure to collapse or the secondary structure to collapse. So by altering the pH, you're altering the hydrogen ion concentration that the enzyme is used to being in, and that means it might start forming hydrogen bonds with the actual solution it's in, not within itself. That interferes, and then what happens is the shape of the enzyme and then thus the active site changes. It has a direct effect on the active site, as you know. So we talked about the induced hypothesis, saying the lock and key theory is the idea they're perfectly complementary, but the active site and the induced fit hypothesis relies on charges being in the right place, matching up with opposite charges of the substrate, so they stick together perfectly. And if you put in hydrogen bonds, in hydrogen, extra hydrogens in there, or take hydrogens away if you're making it less acidic, that could alter the charges that are interacting with the R groups, the amino acids, and it could alter the substrate binding with the active site. So that's obviously pretty important. So you might get a graph like this. So this graph sort of shows you how pH affects the reaction rate. So it's unlikely you're just going to get something like this and have to talk through it like you would with temperature. You're only expected to know the idea of different hydrogen ion concentrations affecting the hydrogen bonding, which then alters the shape and the active site. You're not expected to be able to give specific examples as you would expect with low and high temperatures. But this graph is quite realistic at the bottom. So you've got pepsin, which is a type of protease in the stomach. You could be asked, why is pepsin got a lower optimum pH than trypsin? Trypsin is an enzyme that occurs in the small intestines, about pH 7, pH 8 optimum, and the trypsin is therefore going to have a different set of bonds, and it's going to be, if you put it with a pepsin in high pH stomach, its hydrogen bonds would interact with the acid, so it would be denatured because its active site would change shape. So how else could we change the rate of enzyme concentration other than temperature and pH? Well, we could alter the concentration. So if we have a look at this graph before I put any writing up, you need to be able to read these graphs and read them quite clearly. So what this graph shows us is the rate of reaction, okay, which is on the y-axis here, at differing substrate concentrations. Now, just to make this really, really easy, I'm going to just do it as if there was, I don't know, a 10% substrate concentration there. Let's go for a 20% substrate concentration there, a 30% substrate concentration there, and let's say a 40% substrate concentration there. Now, obviously, I'm doing this on the computer, so it's not neat as it should be, but we'll use that. What this is showing us is as we go from 0 to 10 to 20, and then just above 20 to about this point here, as I increase the substrate concentration, my rate of reaction increases. Okay, and that is showing me that at that point, above, until this line here, substrate concentration in this reaction is the limiting factor. It is the thing that if I add more substrate concentration to the mixture, I will have an increased rate of reaction. So substrate is the factor alone that is limiting the rate of whatever this reaction is. However, and why is that limited here? If we think about it to start off, sorry, if you've got more substrate, you keep adding more substrates there, it's like more fuel for a reaction, it's more ingredients, you'll get more of the products as a result. However, after this line, at this point here on the graph, that doesn't work. And the reason that doesn't work after that line is because something else has become the limiting factor. So what will happen with substrates are that the substrate, if you keep adding substrate, great, the reaction keeps going up, but at some point you will use up all of the enzymes and all of the active sites. So after this, at this line, when it plateaus, the substrate is no longer the limiting factor. It's actually the concentration of enzymes. And you can see that because if I increase from 30 to 40 in substrate concentration, it makes no difference to the rate of reaction. The rate of reaction is flat. So what do you need to know? You need to know we can alter substrate concentration, we keep the enzyme substrate concentration, so the enzyme concentration the same in some experiments. As you increase the substrate concentration, you will get more collisions, obviously, meaning you get more enzyme substrate complexes. And again, I'm pointing out this term that you need to use in all exam questions on enzymes. And therefore you get a faster rate of reaction. But and the limiting factor is if all of the conditions are kept constant, increasing the limiting factor will increase your rate of reaction. So the limiting factor before the line is the substrate concentration, but after the line, all the active sites of the enzymes become occupied. So adding substrate will have no effect. So enzymes have become the limiting factor in that case because they cannot, it doesn't matter how much more substrates you've got, if you haven't got the active sites, then it's not going to increase the rate of reaction. What else could you do? Well, you could obviously increase the enzyme concentration. So often you have surplus substrates, but you don't have enough enzymes. So exactly the same that we talked about a few moments ago. This graph here is showing you this now is concentration of enzyme. So until this point here, okay, that is as you increase your enzymes, so does the rate of reaction. But then you obviously run out of substrate. Okay, so the enzyme numbers the rate of reaction will level off because it doesn't matter if you keep adding more and more substrate, enzymes, sorry, it doesn't matter if you haven't got enough substrate, you won't make it any quicker. So it's a bit like if you owned a factory and you were making cakes, let's say, if you employed loads and loads of people to work there, but you didn't have enough ingredients, you wouldn't make any more cakes. But we can add extra substrate often, and therefore the graph often has this dotted line going up as continuing to show what could happen. So what do we need to know? Well, if you increase the enzymes, you get more active sites available. Therefore, you can have more enzyme substrate complexes, and therefore more products happen to a higher rate of reaction. But the substrate numbers become a limiting factor, and adding more substrate will increase the rate of reaction as there are spare enzymes with spare active sites available. Now, when we compare reactions, what you might want to do is look at rates of reaction and actually calculate them. So what we actually do when we calculate rates of reaction is we calculate the initial rate of reaction at its fastest point, and you calculate the gradient. So what you would do is if you were calculating this top line here, is you would get a ruler and you could extend your ruler because it's going to be hard to measure it on the actual line, but you could extend your line using the ruler up, so follow that blue line, and then you've got the value of x and the value of y. So let's say x had a value of 5, okay, and y, which is the time, had a value of 2 seconds. What you then do is x divided by y, which would be 5 divided by 2, so that would equal 2.5 centimeters cubed of gas produced every second. Okay, so x divided by y. The rate of reaction is always fastest at the start, and that's when our product numbers increase the most. Obviously, any reaction, and this is really a GCSE question, any reaction you expect to see that increase, and then it slowly plateau there because the substrates will be used up, and therefore you'd have less to go into the active sites, and that would be that. Okay, so we always use the initial rate, which gives us the maximum rate of reaction, to work out the rate of reaction. Now, the last thing is, so there are two types of inhibitors that we need to talk about, and that is competitive inhibitors and then in a moment non-competitive inhibitors. So let's have a look at competitive inhibitors to start off with. So if you look at the top of this picture, it shows you we've got the substrate in blue, okay, and then a competitive inhibitor is this sort of orangey red shape, okay, and this competitive inhibitor is basically a similar shape to the substrate. It will get into the active site, but it won't react. So what happens is the competitive inhibitor goes in, that then blocks substrate. So they're competing for access to the active site, hence the name. So obviously, if you have loads of substrate, the effect of the competitive inhibitors will drop. If you've got lots of competitive inhibitors, then that will maybe increase the effect of them. So if we have a look at a graph here, this shows substrate concentration, the effect of it. So again, without competitive inhibitor, as you increase your substrate concentration level, the rate of reaction will increase till a certain point when your enzymes become the limiting factor. If you do this with inhibitors present, they will have a slower rate of reaction. But if you do keep adding enough substrate, eventually the substrate numbers will outcompete the competitive inhibitor numbers. But basically, they're competing for the active site. So the more competitive inhibitors, the less substrate, enzyme substrate complexes you're going to make. Now, a non-competitive, your competitive inhibitors are normally temporarily, and they're often reversible because they only just block the active site until they come out again. The non-competitive inhibitors, however, are normally permanent and irreversible, although there are examples in our metabolism where a enzyme at the end of a series of reactions will act as a non-competitive inhibitor and change the shape of the original enzyme, which you might do about in class. But today, a non-competitive inhibitor is an enzyme, so this green one here, which attaches to somewhere called the allosteric site, which the word isn't on this slide, unfortunately, but an allosteric site is a site somewhere other than the active site. So you see they've represented it here, that the green molecule, the non-competitive inhibitor, attaches to the enzyme at the allosteric site somewhere other than the active site. That then changes the shape of the active site, so the substrate molecule can no longer bind. So it doesn't matter if you've got a million substrate molecules or just one substrate molecule, your rate of reaction will stop if you've got non-competitive inhibitors, because you will change the shape of the active site, and that will then stop the reaction happening, stopping you from enzyme substrate complexes. Okay, so that's been useful for you guys, and I'll see you again soon.